life cycle inventory and cost analysis of alternative concrete pavements. So this was part of Helen's research. And also, and then again, as you notice, these are two distinct systems, two distinct components of the same built environment system. Okay, so we're looking at energy efficiency in buildings. And also, as we look at each of these, we see that it's not just limited to, so for example, when we're just looking at design, we're limiting it to the very material aspect of the built environment. But then we also go on to risk assessment, which impacts a societal component, which is where we're looking at alternative designs on impact of alternative designs on bidding. So what competitive advantage would it give a contractor in terms of what they're providing, the services they're providing, and ultimately is it a win-win situation for the owner and the contractor. And then also, as we look at these systems, what are the long-term behaviors of some of these infrastructure systems? We have aging infrastructure, and more often than not, what are our failure rates like, and how do we understand performance of these systems? Because good performance, or at least sustainable performance, is critical to reducing impacts. So just a brief overview, and I've presented this work before at similar forums, so I'm not going to go into detail, but just an idea of what this would provide us is the impacts of alternative materials such as fly ash and slag in reducing life cycle emissions. So we find that for jointed plane concrete pavements as well as for continuously reinforced concrete pavements, and as you include fly ash and slag in the in the cement mix, what you realize is that it significantly reduces emissions over the life cycle of the pavement. So this is very simple. It's a simple feedback that you can use into your design and say, you know what, we want to go up to a higher percentage of fly ash or slag. Of course, it creates other problems in terms of performance. And so far, what we've been looking at is primarily at the material composition, alternative materials, and also a little bit of maintenance costs. So you realize that both the pavements have comparable impacts during their construction phase. But when it comes to long-term life cycle costs, we realize that even though CRCP pavements are continuously reinforced, they're much stronger, a lot more steel, they have a relatively much longer lifetimes and require much fewer maintenance cycles than jointed plane requires, which has less steel and you would expect to have a lesser impact than CRCP. And then again, these are just two parts of the general idea of how do you create a sustainable transportation infrastructure. And then so as we go on towards the end, I'll provide more of a plan of where we're headed with this. So of course, one of the big problems in this domain also is that there isn't a lot of existing available data. And Chris and I were very excited. We're just starting on a project with Michigan DOT where hopefully we'll be able to get a lot of, not hopefully, we will be able to get a lot of interesting data that we'll be able to mine into. Now, looking at energy savings for buildings, and this is another example where you can have feedback into static design using alternative roofing systems. We used a green roof, but really, I mean, it could be a traditional roof which has better insulation. So, and what it shows you is that over a life cycle, you get tremendous improvements, and we had a case study too. And in our case study, we were seeing a much higher, this case study was in Grand Rapids, Michigan, much higher margin, but over the average performance, we see significantly improved margins, which could give a contractor significant advantage. And then, of course, we get into the more stochastic long-term behavior of some of these infrastructure systems. So, for example, Yonglang's looking at sewer blockage events. We have 10 years of data for the city of Houghton, which is a really nice toy city to play with because it's small, it's manageable, and it's fun. So we have the sewer network, and what we find is that we are finding parallel relationships, which is to say that how often you're having sewer blockage events to what the intensity of the events are related by a to the power of x, a constant parallel relationship, which is a very interesting find because power laws typically can be used. It's kind of an interesting dead end because power laws show that there are fundamental complexities within the domain and there are emergent. It is really the outcome of an emergent process. But beyond that, it doesn't really take us very far. It requires us to go back to the drawing board to find out, well, what exactly is leading to these blockages? Is it a material problem? Is it a locational problem? Are there other issues that are leading to it? Interestingly, so power law relationships are often found with things as natural as solar flares to things as artificial as website hits. And so now we're finding similar behavior with failures in water distribution networks as well as sewer networks. Where does that take us? Next, we get into, and of course, I'm kind of jumping from point to point here, and we can always go deeper into any of these topics afterwards. Next, we get into the method of representation. So if we can explain all these systems, now how do you create a representational mechanism that would allow us to now look at cost and economic cost, our analysis in terms of environmental impact, and also start asking the question, do we really need to build a road out there? Do we need to add more capacity to this particular highway network? What are the what societal value are we creating? Well, how do you go about doing that? How do you, what mechanism do you use? So, there should be something else here. There it is. Okay, so what the suggestion is, and what we're kind of now using for a lot of our research, is network semantics. We use the idea of a graph. And graph theoretic applications and the application of graph theory in itself it's a very useful paradigm for representing fairly complex information. And for those of you who are not necessarily interested in the mathematical details, really all you have is a set of vertices, a set of edges, and then the vertices and nodes have properties, as do the edges. And you can also think of flow within this graph. So it's ideal for representing multiple different components, each of which could, by the way, have subgraphs that take you into greater detail within it. And it's a great way of showing the constraint relationships, and then there already exists, there's a mine of graph theoretic algorithms that can be used to understand flow within these networks, that can be used to understand the impact of subgraphs on the supergraphs, so micro behavior on macro behavior. So mathematically, this is a gold mine to fall back on. And I'll show you some applications that we've been working on. So functionally, while we're representing all the information, critically it's also helping us to show domain topologies, which is the spatial information within that particular domain. Functionally, we can also start representing impacts across these subnets, and I kind of just spoke about that. And then finally compute. Really, most of our problems come down to computing critical paths. What does resilience within an infrastructure network mean? What does sustainability mean? Resilience, for example, there are ideas of redundancy in a network. And could we use ideas of redundancy in a network to translate into resiliency and sustainability? So, example. So this is City of Houghton. Excuse me. This is the City of Houghton. And what we have here is a very high-level network. So as you notice, we're not looking at all the details of all the streets. We're looking at the major thoroughfares, and we're looking at we're putting in these nodes out here, and I'll tell you in a minute why we have them in different colors. So we have this. We have a transportation network. Very simply, we're looking at directed. It's a directed graph where if you can go from one point to another, there is an arrow in that direction. So if it's a bidirectional arrow, it's a two-way street. Unidirectional arrow, it's a one-way street. And then, of course, you can see, and then the other thing that we can also present at the same time is this is the water distribution network, again at a slightly higher level within the City of Houghton. And you realize that the water distribution network and your transportation network are overlapping. They're overlapping on each other, and an impact on any one of the networks could critically bring the other network down as well. Okay, so